thanks for joining us. So we're happy to have Aaron Turon come join us from Mozilla Research all the way in Portland. So he's coming down to talk a bit about the Rust programming language and some of the research problems that are in that sort of space of programming. So without further ado, I'll let Aaron take it from here.
Cool, thank you so much. I was just telling Zaina I was a student here back in around '09, so it's really exciting to have a chance to return on the other side of things. So yeah, I work on Rust at Mozilla. I actually manage the Rust team there, and I came there out of an academic career studying programming languages at Northeastern University, and then a postdoc with Derek Dreyer. And one of the things I love about Rust is the mixture of sort of hardcore academic theory and literature that comes into play and strong engineering. So it's a programming language that I think really blends these worlds really well. And part of the point of this talk is, now that I'm on the other side and filled with more research problems than my team could possibly tackle, I want to come back to you all and beg you for help. So before I dive into the talk, I just want to get a little sense of the audience. So how many of you have looked at Rust at all, like have any knowledge about, whoa, okay, great. Well, so a bunch of the talk is going to go through some of the basics of Rust, but we may be able to move a little more quickly because of that. And then another question, how many of you are involved or wanting to be involved in some kind of academic research around programming languages? Okay, roughly the same count. Fantastic. Well, we have perfect audience then. So before we dive into sort of the technical meat, I want to frame a little bit what Rust is about, what we're trying to achieve with it. And this framing will sort of fit the rest of the research questions into it. So Rust was started at Mozilla. It's sponsored by Mozilla, but it is an open community project. But Mozilla started it because of their needs for writing the Firefox browser. So prior to Rust, all major browser engines were written in C++. And the reason is that browsers compete very heavily on performance, on overhead, the ability to play the latest kinds of video formats, play the latest kind of games, and so on. They're almost like small operating systems. So the demands are very heavy, and they need a lot of low-level control over the machine to be competitive. But at the same time, browsers are sort of the gateway between your machine and the wild internet. So they're the first point of contact for malicious code that's going to try to exploit the browser and get private data or whatever. So at the same time, they need that low-level control, but ideally they also have safety. But if you have lived in the world for any length of time, you can guess how this usually plays out, which is the speed and performance aspects win the day because they are sort of the obvious things that you see when you first download a browser. And the safety aspects fall by the wayside because, well, maybe you'll get hacked eventually, right? But it's not something that's as readily apparent. But Mozilla cares very deeply about this, and browsers do compete to some degree on safety. So the idea with Rust is to give a language that gives you the level of control that a browser needs, but has far better safety properties than a language like C++. And I think, at least in industrial work, this was always seen as a trade-off. You can go low level and get that control, but you would always be giving up safety. And there's been a long line of academic work with languages like Cyclone that try to get both of these properties together, and basically Rust is a sort of industrial application of those ideas that's actually getting mainstream adoption. And it goes hand in hand with the Servo browser engine, which is also sort of originally a piece of research. Now components of that actually ship in the real Firefox browser. So Rust is used in Firefox today. Okay, so that's the really high level pitch. But I want to give a little bit more technical detail because it'll be useful for explaining some of the mechanisms of Rust later on. And so I don't know how rusty hot your C++ might be. So I'm going to walk through a couple ways that C++ offers control and a couple ways that it does not offer safety. And then we'll see later on how Rust sort of gives you both. OK, so here's a little bit of C++ code. First thing to notice is in a language like C++, you have extremely fine-grained control over things like memory layout. So when you create a variable like this vector, you know, first of all, something's going to live directly on the stack. And it's not just a pointer. There's actually a bunch of metadata about the vector that gets allocated directly on the stack. Stack allocations are desirable. They're faster. And furthermore, there's only one level of indirection from what's living on the stack to the actual data in the vector. Right, and if you compare this to most garbage-collected safe languages, something like Java or C#, you would have several layers of indirection. Everything is a pointer, basically, to make everything have uniform size and make it easy for the garbage collector. Right, so this kind of thing is very important if you're trying to watch cache locality and memory size and so on. So that's one thing you get with a language like C++. And notice here, thinking about this indirection point, so this is a vector of strings, and of course strings themselves are a container of characters. So we actually have two levels of nesting, and the nice thing is the same property of the metadata being allocated directly instead of being behind a pointer repeats in this nested fashion. So to get to a character of the string inside the vector, you only have to go through 2 hops, which is basically the least possible number of hops. Okay, so the layout is one aspect. Another aspect that is closely related is the ability to work with references, which you can think of as pointers for this discussion, but references directly into an object. Again, in garbage collected languages, you don't tend to have this kind of facility. You don't get to point into the interior or something. You always have to point to a whole object. And this kind of thing is again, very important for low-level programming. Finally, there's a bit of code that's not there, which is when you leave the end of the scope, the vector goes out of scope and is automatically deallocated at that point. In general, there's no garbage collector in C++. You have deterministic destruction. So you know statically, looking at the code, when a destructor is going to be run precisely, and that gives you very predictable performance. So those are the good things, or some of the good things about C++ that we want to retain. Here are some of the things about C++ we don't want to retain. So playing with the same sort of example, we're now going to take one of these references to the interior data in the vector, and then we will mutate the vector. And in this case, what we're going to do, let's imagine that this vector only had capacity for one element initially. So in order to add another element, we're going to have to allocate a fresh buffer and swing the pointer over. OK, fine. So we allocate the buffer, we copy the existing data, we push the new data. That all seems good. Now we swing the data pointer over. OK, this all makes sense. But we're left with this reference we took earlier, which is now a dangling pointer, right? It's pointing to the original buffer and has no knowledge that anything has changed behind its back. Now, modern C++ compilers are actually pretty decent at catching really obvious cases like this. They have some amount of static analysis, but they can't provide strong guarantees about this in every case. And any mistake like this is part of the attack surface of a browser, right? So any mistake like this is a potential way that a hacker could get in, take control of the browser, and get your credit card number. And so in particular, if we have this dangling pointer and we later try to use the element, things can go haywire, basically. The C++ spec says anything could happen. Now, this is a pretty simple-minded example, but it actually shows off 2 key things that you need to create this kind of bad situation. And those 2 key things are really central to Rust's model of ownership, which is one of the foundational aspects of the language. So the first thing that was going on here is we have aliasing. So we have multiple pointers pointing at the same thing. Aliasing by itself is not a problem, But when you combine it with mutation, it can be a problem, right? And so what happened here is we had two things that were aliased, and then we mutated one of the aliases, but we had no idea that there was this other outstanding alias. It wasn't updated in any way, and so things went off the rails. And so we'll keep coming back over and over in the talk to this idea that it's mutation plus aliasing that gets us into trouble, and Rust basically gives you lots of ways to have one or the other at a time, but only in carefully controlled ways do you ever get both at the same time. By the way, please ask questions at any point if you have them. All right, this is the last bit of C++ we will see. So a lot of the problems I just highlighted, if you're coming from the perspective of higher level languages, you might think, well, garbage collection solves all of this, and we have pretty decent garbage collectors out there. So there are a couple of problems with this. First of all, while you can get away with a garbage collector in a lot of domains, it doesn't work everywhere, and it's a non-starter for a browser for any number of reasons. I mean, even as it is, people complain a lot about the memory footprint of Chrome and Firefox, even though they are deterministically deallocating memory. If they were using garbage collection, I think it would be a lot worse. Plus, you'd have unpredictable pause times. It limits the language in some other ways that we also care about. But I think even more interesting is that garbage collection only solves one particular slice of this kind of problem, but there are actually a ton of highly related problems that all come back to this combination of mutation and aliasing, but not all of them are solved by a garbage collector. I won't be talking about concurrency really at all today, unfortunately, but except for this slide, which mentions data races, which are sort of a kind of race condition that is universally a bug. And data races fundamentally have to do with aliasing, mutation, and a lack of synchronization. So garbage collectors don't actually give you any help with concurrency, other than the fact that you're at least guaranteed that whatever you tried to access is still there in memory, but you might still be racing with other threads to access it. So the neat thing about Rust is it solves these kinds of problems in a different way from garbage collection that also addresses a whole bunch of other kinds of problems that garbage collectors don't get at. So I mentioned Cyclone before. You can roughly think of Rust's heritage like this. So we have sort of traditional systems programming represented by C and C++, which are very different languages, but so be it. Cyclone has a lot of the core ideas that Rust uses to attack the problems I've been talking about. And then we mix in a lot of ideas from the functional programming tradition, ML and Haskell. And we'll see pieces of all of this as we go through the talk. To try to sum up very briefly what Rust is if you are a well-versed sort of PL person. So I basically think of it as two main ingredients, and the rest is just details. The first ingredient is its ownership system, which is fundamentally an affine type system. So that's like linear types, but you are not required to use a piece of data. We'll talk about that a bit later. But then it also has a system of borrowing, and we'll be going through that pretty extensively. So ownership is one major pillar that's based on substructural typing. And then the other major pillar is what we call traits in Rust, which are very similar to type classes in Haskell, although there are some differences. And other than that, it's just sort of you mix those ideas up with a bunch of the kinds of things that you might expect from a modern language. So type inference, algebraic data types, pattern matching, so on and so forth. And that's pretty much Rust. So the nice thing is the structure of this talk, I'm basically going to talk about ownership and the trait system in two halves in the talk, and cover both what they are and some open research questions around each of them. So over the course of the talk, you will see basically the core of Rust all the way up to the frontier of what we're trying to figure out. Right, so just to summarize all of that, ownership and borrowing is really the most important innovation in Rust. And it implies that you don't need a runtime, you get this low-level control, which is something that you get from C++. It gives you memory safety, right? So you don't get use after free, dangling pointers, stuff like that. That's something you could get from a GC, but it also gives you things like data race freedom, which none of these other languages do. And it gives you all of those things through that single mechanism of ownership and borrowing, which is what I'm going to talk about next. Any questions so far? All right, let's dive in. So I mentioned before this idea that it's the combination of aliasing and mutation that gets us into trouble. And that insight sort of explains the basic Rust ownership system. So what we're going to do is walk through a bunch of different types in Rust and understand in which cases you get to alias, in which cases you get to mutate, and how Rust manages that. So the first thing is, if you just have a type, just by itself, no special annotations, like vec of t or something, that represents an owned value. So if I pass you a vector, I have relinquished my ownership of it and transferred ownership to you. And that specifically means I can't keep an alias to that vector anymore. I've given up all access that I had to it. And so we don't have aliasing with owned values, but then on the flip side, if you have an owned vector, then of course you can mutate it. You're the only person with access, so you can do whatever you want to it. Okay, so let's actually see that with some code. So this is actual Rust code. So we have a function give, and that's going to allocate a new vector, push a couple elements, and transfer ownership. And we'll walk through the actual representation details just to tie it back to the C++ model, right? So like C++, we know that this vector is going to be allocated on the stack, which means we have sort of its core metadata, a pointer to the buffer, the actual length, the capacity, and so on. Great. Now, as we push elements onto it, same as with C++, we'll get this pointer off to, we'll actually allocate a buffer and start adding some elements to it. Okay, great. So the interesting thing, the place where ownership comes in is when we actually pass this vector to another function. So if you notice, the type of the parameter to take, as I said, is just plain vec of int. And so an undecorated type means an owned value, so we're transferring ownership of the vector. So what that actually means in terms of representation is we're going to make a new copy of the stack data around the vector. That's the stack frame for the take function. And we're basically going to disallow access to the old stack data that we had in the give function, right? So we don't copy the whole vector, right? It's only this sort of like crust of it, the immediately owned piece. We copy that over, and then we relinquish access to the copy that we originally had. So then take can go do whatever it wants with the vector, and crucially, now this comes back to the whole destructor point in C++ and the affine type system. We can leave this function without ever having used up vec, and what will happen is the destructor will run at the end. So if we don't transfer ownership to someone else, if we're the last, we're the one left holding the bag, then when we exit take, the vector is actually deallocated, right? So the buffer goes away, and of course the stack frame is popped. But we do still have this old stack frame for give, right? So far, like all of this would look the same in C++, right? So what's the core difference? Well, the core difference is that the compiler actually checks ownership, right? So these things I'm telling you, these concepts of ownership transfer are actually part of the type system. And so in particular, if we tried to access the vector through the existing stack alias we had before, the compiler would complain and say that you can't do that, the vec has been moved on the previous line. You transferred ownership of vec, you no longer have access to it. And unlike the sort of simple static analyses that C++ compilers sometimes do, the idea here is guaranteed safety across the board, right? So this is not just catching simple cases, this is catching 100% of the cases. And so this kind of thing rules out any number of common bugs from C++, use after free, double moves, data races, and so on. And it's the simplest model of ownership in Rust. So this is just basic affine typing, yeah. You don't get the same static guarantees, no. You get more help, but there are ways to write unsafe code with it in C++. Right? There's no actual static guarantee. Right. So just to make sure everybody heard, like, so C++ has also been evolving, and so-called modern C++ has some number of features that capture some of these ideas around ownership. Some of them rely on runtime checking. Some of them do give a certain amount of static checking, but there's no actual hard guarantee around memory safety, and there's no interfacing with concurrency again. Another question?
In the previous slide, you had this movement of the metadata, copy of the metadata. So
Yeah.
what is the previous copy maintained in the function?
Sorry, you're asking why is it maintained?
Yeah.
It's just the stack frame, right? So yeah, it's as simple as that. Right. So generally you allocate and deallocate those in a big chunk coming in and coming out. Yeah.
You said you're not copying the entire vector, just so how this will work. So if some function want to access some element of the vector, when it's in give function, it's not there in the thing.
Sorry, I didn't quite catch that.
Okay, so you are giving you're copying this vector from one location in this set to another location, but not the complete vector.
Yes.
So now if there is some function who want to access inside the thing some element of the vector,
Yes.
how this will happen since you didn't copy
I see. Okay, so yeah, just to repeat the question. So I was saying earlier that when we transfer ownership, that doesn't mean that we're copying the entire vector over. There's just a little bit of data that lives on the stack. But if that's the case, then how does it actually work for take to access elements of the vector? It doesn't have its own copy. So the point is, the distinction here is sort of between stack data and heap data. So things that you allocate directly versus things that are allocated behind a pointer on the heap. And so when you transfer ownership, or move, as we call it in Rust, you only transfer the stack data, but it has a pointer to the pre-existing heap data. And the key point is, when we do this movement, we know that this new pointer, here, let me get to the right place in the slide. Okay, right, so we make a copy like this, but then we know that this new pointer, which is pointing to the existing data, we know that that's the only pointer that's valid for use at this point. So we know this is the only way to actually access the buffer, and that's what rules out some of the safety problems we saw earlier. So that's the sense in which we've transferred ownership. We've got these two pointers existing in memory, but we're saying you're only allowed to use this newer pointer, so it sort of owns the data that it points to. It can do whatever it wants with that data. And it's guaranteed that no other pointer can be used behind its back to deallocate the data or something like that.
Do you have threads in Rust?
Yes, we have threads in Rust.
How does it work in terms of multiple threads?
Sure. So how this works for multi-threading is actually exactly the same. So you could do this same example where instead of making a function call, you were passing vec through a channel. And what that would do is exactly what's happening here. It would take this metadata, the sort of directly stack allocated data for the vector, and send that through the channel. So basically send the pointer through the channel. And then on the other side, the receiver would move that data onto its stack frame. then you'd end up with exactly this picture, except that instead of being sort of lined up on one thread stack, you now have two different stacks. But the key point is the original thread has given up ownership in the same way that give, the function give here, has given up ownership.
Child threads can access at the same time.
One more time.
Child threads can access at the same time.
So with ownership, threads only one thread can access a piece of data at a time. And more generally, there can only be one active path, one active alias to get to a piece of data at a time. So, we can have a bunch of threads that are interacting and they're passing pointers to each other over channels, but whoever was the last one to actually get the data is the only thread that's allowed to actually use that data afterwards for this simple ownership transfer. Does that make sense? Sure. Yeah.
This example, can take as the ownership to the give function?
Okay, so yeah, question is, could ownership go the other way? Can take call give? So yeah, absolutely. I mean, here give doesn't take an argument, right? Give is just allocating a vector. But if you imagine some other function that took a vector as an argument, take could call that, and that could call another. You can nest this arbitrarily.
But the give function no longer can have the ownership of the vector.
Right, so the point is, when we're talking about functions calling each other, right? So the give function is more or less paused at this point, yeah? So I see, so maybe I was confused by the phrasing. Maybe what you're asking is not so much can take call give, but rather can take return ownership of the vector to give. Yes, it can. So the simplest way to do that is to literally have as the return type a vec event and just return that as the value, and then take that back in the give function. And you might imagine that that's what you would often do, since most of the time you don't actually want to give up ownership when you pass something. But that would be a very painful way to program. So we'll see in a minute the system of borrowing that sort of gets at that same idea, but in a nicer way. Yeah.
First line of give is that the keyword implied that is immutable if mute is not there.
Yes, but not in any particularly deep way. That's more of just a sort of helpful aid. I don't know. I don't want to go into that too much. Let's just gloss over that point. Other questions? Cool. Okay. Now you get to see that again. Okay. Right. So, yeah. So going back, right. So this key difference from C++ is that you have a completely dependable static analysis that can make strong guarantees around memory safety and data races and other things. So you're guaranteed that there's no way you could possibly still have access to this vec after you've transferred ownership. All right, so that's the basic ownership system, and if you know things like linear types, it hopefully seems at least somewhat familiar. But as we were mentioning earlier, this pure ownership system by itself is a little bit painful to program with because a lot of the time you don't actually want to transfer ownership, you want to give temporary access, but retain ownership for yourself afterwards. And so that's where the concept of borrowing comes in. There are two kinds of borrows in Rust, shared and mutable borrows. And they basically differ in terms of shared gives you the ability to alias but not mutate, and mutable the other way around. And so the way we write that type is just ampersand t, that's a shared reference to t. And so let's walk through an example of that, and then we'll come back and look at mutable references. Okay, so this is very similar to the code we were just looking at. So again, allocating a vector, pushing some elements onto it, great. But now, when instead of give, right, we're calling this function use, and instead of it taking a vec event, it's taking a reference to a vector. And so what this is saying is the use function doesn't require full ownership of vec to do its work. It's happy to just have a reference to a vec that it's allowed to use while it runs, sort of gives up rights to at the end. Right, and at runtime, this is just a pointer. And on the other side, where on the call site, we also write an ampersand designating that we're not transferring ownership of vec. We are instead temporarily borrowing vec, giving it to, handing that borrow, sort of lending it to use, and then continuing on. Right, so let's see a little bit more how that looks at runtime. So it's different here in that we don't, if we look at use, the stack frame for use, it doesn't have that full copy of the vector's stack data because it doesn't have ownership of the vector. Instead, it just has a single pointer back to the original stack frame, which is still intact. And what, we go ahead and execute use. We can read the vector through this shared reference. And then when we exit use, its stack frame is discarded, but that does not involve deallocating the vector, unlike before. All we're discarding is a reference to a vector, a borrow of a vector. It doesn't affect the underlying data at all. And so the key point is that now the lender function can go on to mutate the vector, access it, do whatever it wants. It's retained ownership. It only gave up its own ownership temporarily for the duration of this function call. Make sense? Okay. So, I mentioned shared references give you aliasing but not mutability. So if we think about things we might want to write in a function like use, you could imagine, we'll try to push onto the vector or modify one of its elements. And similar to before, the compiler will catch all of these attempts and basically say, you don't have sufficient access to the vector to do that operation. You only have a shared reference, so you can't mutate the vector. And so this is, if we go way back to the C++ example where we were taking a reference to a vector, and then while that reference was hanging out, we mutated the vector. That's what sort of caused the problem of a dangling pointer. And in Rust, what happens is when you've taken a borrow, while that borrow is around, you're not allowed to use the original alias to the data structure. It's effectively frozen, but you can hand out all copies of this shared reference all you like. They can be used to read the data but not mutate it. And then once all of those borrows have expired because the function call ended or whatever, then you go back to full ownership of the data again. And there are various asterisks here. I mean, most of what I'm showing you, and we'll see this a bit later, there are controlled ways to work around. But this is, these restrictions I'm talking about are the default way of programming in Rust. And most applications can get by using this methodology completely, sort of completely safe Rust. So any questions on shared references? Yeah.
Is this like, for instance, parameters in C?
I mean, sort of. So the question was, is it like constant pointers in C++? I mean, I don't really know. I guess I should say no, in the sense that the guarantees here are much stronger. It's like getting at the same idea, but in Rust, the difference is all these things have much deeper meaning to the compiler and type system, so we get strong guarantees about what you can do with them. Yep.
So the compiler must be determining that pushes the mutation, right?
Yes.
But aren't there instances, where the behavior of push, whether it's mutating or not mutating, can be dynamic?
Yes.
So the compiler errors on the safe side saying mutation might occur depending on which branch is taken.
Yeah. So I'm repeating all the questions for the video. So the question here is, if the compiler is reasoning statically about the ability to mutate, what happens if whether you mutate or not is actually a dynamic decision. And that's a great question. So generally, a method like push will have a way that it takes its self argument, and it can be as an owned value, as a shared borrow, or as a mutable borrow. So each method has to decide once and for all statically what kind of borrow it's demanding. And so that means if there's any possibility that use would mutate the vector, then it needs to arrange to have mutable access sort of statically at the top. But of course, there's more to the story. So there are tons of library types in the standard library that let you push various things to runtime, for example. So you can set things up where ownership only might be used at runtime, and it's sort of checked at runtime whether you've actually gotten that right and haven't accidentally created aliasing and mutation at the same time. So again, what I'm showing here is the default methodology, which gets you surprisingly far, but then there are tons and tons of ways to sort of bend these rules, and we'll see examples of that later. All right, anything else? Cool. Great, so then to complete this part of the story, the other main type is a mutable reference. And here, you can only have one of them active to a given piece of data at a time, so no aliasing. But when you hand out a mutable reference, you're handing out the ability to mutate the data. You don't, however, hand out the ability to destroy the data. That's the key difference between mutable reference and owned data. So here's a simple example that's pulling some of these concepts together. So this is a function that's just copying the contents of one vector to another. So the source vector, we only need read access to. So we just take a shared reference. The destination vector, we need mutable access, so we take a mutable reference. Fine. Because we have mutable access, we are allowed to call push on the target vector. Great. And the way this is going to work, as you'd expect, is as we go through this iteration, LM here is basically going to be a reference to an element in the source vector, a shared reference. And of course, from and to themselves are both references. So LM here is pointing to the first element of the vector, and then star LM is making essentially a copy of that integer. So great. Okay, so we go one element at a time, updating the reference each time, pushing it onto the other vector. This is all very simple. But if you're thinking hard about this, you might spot a problem that code like this could have in, say, C++, which is if you called this function with the same vector for source and target, you could create the same situation of aliasing and mutation together, dangling pointers, and all the rest. And so in particular, right, it might be that at the first push we made, we had to reallocate the buffer to make space, and now the existing LM pointer is no longer valid and things break. Yeah, dangling pointer. Okay, so how does Rust deal with this? So we have to go to the call site to see the answer. So here we have some function that is going to call push all. It has owned access to a vector in whatever way, and it's trying to take a shared reference and a mutable reference to that vector at the same time and pass it to push all. All right, so we have this first shared reference, but the compiler will give us an error on the mutable reference, basically saying you can't lend out the vector in both ways at the same time. And that's what it means for mutable references to not allow aliasing. Now, what we can do, right, we can say &vec multiple times. We can hand out multiple shared references to the same vector. That's read-only. That's totally fine. But we're not allowed to ever combine multiple borrows if one of them is mutating. Cool. So that rules out sort of this bad situation. And it leads to a general property that mutable borrow represents the sole way of accessing a piece of data for the duration of that borrow. And I'm going to dig into each of the pieces of that a little bit to lead up to this first research question. So let's look real quick at a somewhat more complicated example to get deeper flavor for how Rust is actually checking all this stuff. So here we're allocating a vector, right, we're doing some computation sort of for each element in the vector and then attempting to push more data over the course of this loop. And notice this loop is written a little differently, so it's instead of iterating directly over the elements, it's just iterating over numbers, right? So there isn't this borrow of the vector being made outside to get the elements. It's all happening inside the loop body. So this looks bad for all the same reasons that we've been talking about before. So we have references floating around, but then we're mutating the data. Seems, this is that combination we're always trying to rule out. So to explain how Rust's compiler sees this, when you take the original shared borrow of vec I, that borrow is understood to last for the rest of the scope. Right, the same way we talked about destructors earlier run at the end of the scope, borrows also end at the end of the scope. And so that borrow persists over this attempt to push. And that's what's going to let Rust catch this bug, because when we see this later piece of code, we know it's within this region that the borrowing is happening. And again, we can say, well, you already have a shared borrow of vec. You can't also now take a mutable borrow, which is what you need for the push method. So I should say methods have some special sort of sugar going on. So we don't actually have to write ampersand mute vec to call push. That happens automatically because the push method has said it needs that kind of borrow. But anyway, Rust is tracking all this. And so it rules this out. On the other hand, if we do this push outside the scope of the loop, that's fine. And the reason is, we know that none of the references we took inside the loop could persist across the actual body of the loop. In other words, Rust is checking that those references only live for as long as one iteration of the loop. They never escape. And so we never have this combination of aliasing and mutation. Okay. Right. So I guess the other thing to say here is this is also based on a notion of paths. So here the path is really simple. It's just vec, the name vec. So that's the direct piece of data on the stack that we're borrowing. But in general, vec could be a compound data structure with fields inside it. And in those cases, we can borrow each field independently, and Rust will track the way that each of those paths is borrowed for each region. Okay, so not super important to understand all of these details, but I just want to give you some sense of how borrow checking in Rust actually works. Questions? Cool. Oh. I am not going to talk about concurrency at all.
Because if inside the loop, if you bought like loan out the borrow, then how the compiler tracks it?
Right. So I think the question is basically like, if we were, say, sending a reference to another thread inside the loop body, like that could be one way that it escapes, and that would be bad. That would break these invariants. The basic answer is that things like channels know how to reason about borrows, and so they will impose constraints like, for you to send a piece of data on this channel, that data cannot have any borrows inside it. And that actually is a good segue to the next slide. So these types we've been talking about of these two different borrow types, usually we just write ampersand t or ampersand mute t, but there's actually more information being tracked by the compiler, and sometimes we have to talk about it when we're writing code as well, which is this idea of a lifetime. So we represent that as tick some name. So this is just a lifetime A. And you can think of a lifetime as just describing that gray region of code, basically like a static block of code for which a borrow is being taken. So as we're passing all these references around, what the compiler is doing is tagging all of them with the region of code that they correspond to. And that's how it can do things like make sure you don't send one of these borrows to another thread, because the channel abstraction will say, oh, all lifetimes in this data must outlive everything, must be basically tick static, as we call it, a special lifetime that essentially means no borrows inside. And so we build up abstractions like that use these kinds of lifetime constraints to extend what the language can do, but keep its safety properties. Yeah.
If there's enough interest, I can try on next Tuesday to give an overview of how concurrency works in Rust and relate it to what Aaron's talking about now.
I would even be happy to share a slide deck that does exactly that.
That would be
Cool. Remind me at the end, and I'll send it to you. All right. I need to speed up. I'm going to sort of blow through this section real quick. So the interesting thing is now I've revealed to you that these lifetimes are sort of flying around, but we haven't had to write them, but they're there. So when we write a function like this, use, that says it's taking a shared borrow of a vector, what's actually happening is there are some rules that say, oh, when you didn't write a lifetime, the way that's interpreted is you don't care what the lifetime is. So we'll just say the function can take a borrow of an arbitrary lifetime. And so basically we're saying, I don't care what what region of access my caller has to the vector it's handing me. All I care about is that it's good enough for me. Basically that this lifetime is big enough to cover this call. And that's just always the case in Rust. Anytime you can pass data to a function, it's required to sort of live long enough for that function. And then things get more interesting if we're returning borrowed data. So in a case like this, where we're just projecting the first element out of a vector. So here, the default interpretation is to say, well, if we're claiming to return some borrowed data, that data has to come from a borrow that we were given, essentially. In other words, when we leave this function, we're going to be deallocating its stack frame. So if we're claiming to return a reference to something, that thing had better live in some previous stack frame. Because if it lived in our stack frame, it would be gone at the end, right? And so that means usually when you're returning borrowed data, the way that you make that happen is you took a reference to some data that lived higher up in the stack, and you're basically just using that reference to construct a new reference. But the borrowing sort of persists for the same amount of time. So in other words, if you call this first function, you have to take a borrow of a vector to do so, and then you're going to get a borrow of a string back. So you went from a vector to a string, but the string you get is something that lived in the vector. And it's a borrowed reference to that string. Its lifetime is the same as the borrow you originally took. In other words, it's valid to access that string for as long as it was valid to access the vector. Right? They're basically the same as far as the compiler is concerned. Okay, so yeah, I sort of already alluded to this, that if you have structured data, the borrow tracking is actually done on a per field basis. So I'm going to kind of skip through this. But the core rule is, the compiler is reasoning about these field accesses, and if you attempt to access fields in overlapping regions of code, then either the way that you're accessing them must be as a shared reference, so allowing aliasing, or you must actually be accessing disjoint fields, so no overlap in the memory. That's the core. This is basically, a more formal way of getting at you can't have aliasing and mutation at the same time. Right. So we're just about done with the ownership section. So I'm going to, with all of that material, and you don't have to understand it 100%, but again, the goal here is to give you a flavor. We now have enough to see some of the interesting challenges that arise in Rust and scaling it up. So let's take a function that is given access to what we call a slice in Rust. So this is not a vector, but rather just a view into some portion of a vector. So you've got access to some chunk of a buffer. And what you want to do is, given sort of a mutable reference to some chunk of a buffer, you want to split it into two mutable references that don't overlap, right, given some midpoint. So we're just taking a big view of a buffer and breaking it into two smaller non-overlapping views. But the key thing is, we want the compiler to be okay with the fact that we came in with one mutable borrow and we ended with two mutable borrows. And for the compiler to be okay with that, it needs to know that no aliasing is happening. Or sorry, that no aliasing is happening because these mutable borrows allow you to mutate, right? So they better not be aliasing. Okay, so that's what we're trying to achieve. And you might hope that you could write something like this, and don't worry too much about the notation, but this would basically be, please take a subslice of the data from 0 to the midpoint, and take another subslice from the midpoint onward, and mutably borrow both of those, right? This is like logically what's happening. But the compiler actually won't accept this. And the reason is, to accept something like this, we would be asking the compiler to understand arithmetic in general, right? This is a trivial case where, okay, we're just dividing by this midpoint or whatever, but we could be doing something way more complicated in figuring out how to divvy up this slice. And so to get consistent, to get the compiler to understand arbitrary code like this, it would have to be really smart, much smarter than what I've been showing you so far, where it's just reasoning about fields in a structure. So the approach Rust takes here, and this is something it does over and over in its design, is we have this basic set of mechanisms that I've been describing to you, and then an escape hatch of being able to write bits of unsafe code. But the basic mechanisms are powerful enough that you can encapsulate the unsafe code and basically extend what Rust is capable of doing. And that's what I'm going to show you how to do for this example. Right? So very roughly speaking, we're going to write an unsafe block inside this function implementation. And when we do so, we're giving up some of the guarantees around Rust, right? We're effectively writing some C code here. We're not getting as much checking. We need to do this because the compiler is not smart enough to understand the aliasing that's going on here. But the key is, if we do our job right and we audit this function, then we get a guarantee that says, no matter what arguments you pass this function, it will always produce results that fit into Rust's type system. In other words, which basically just means whatever two slices we return cannot in fact be overlapping. As long as we guarantee that, then this function is safe for anybody to call. So it uses some unsafety inside, but we've sealed it up and we've made it so that there's no way to misuse this function and get unsafe behavior. And so in that way, if everybody else is writing safe Rust code and maybe calling this split function, they're still getting all the guarantees around Rust safety, right? So this is like a really, really core principle in Rust that allows us to scale up the approach where we build these safe abstractions that use unsafe internally, but don't expose that to the clients. Does that make sense? Yeah.
You said if anybody else is writing safe Rust code.
Yes.
But that wouldn't be for sealing the unsafe safety operative. So someone else is writing unsafe Rust code, which is also properly sealed.
Yes.
Then do you get the safety property still? Or is that more
Right. Yeah. So the question is, the way I phrased it sounds like, oh, well, you can add unsafety in one piece only, and we still require everything else to be safe. But in fact, you want lots of these little safe abstractions running around. So I don't. I'm not sure how best to formulate that as a theoretical statement. I think it's a very interesting thing, and we'll talk a bit later about a project that has been trying to formally verify some of this stuff. But intuitively, that is indeed what I'm trying to say, is that you've got a bunch of modules, each of which has some unsafe internally, but I guess they're each assuming that their callers, that basically if you write a type like this mutable slice coming in, that the properties you'd expect of that type from Rust hold. So whatever other unsafety is happening, it must also be encapsulated. Anything else? Okay. So the interesting thing is, even for a function as simple as split all, or split that we just saw, there are lots of pretty tricky questions. So one thing that we generally want to do in a compiler is optimize code. That optimization is often based on aliasing information. So if we know that certain variables don't alias, we might be able to reorder or remove, redundant reads or whatever. Ideally, we have this extremely rich information about aliasing from Rust's type system. We would like to use that in optimizations. But if we have unsafe code floating around, it's not clear that the things the types seem to be saying are true 100% of the time. Like maybe they're not true for a little while inside of this abstraction barrier, and by the time you exit the function, everything's hunky-dory, but maybe you violate some of these invariants inside. And so this is the first really big research question that I wanted to talk about, that we're looking at actively right now, which is essentially how do we negotiate between the desire to optimize and the desire to have confidence in the unsafe code we're writing. So this is, if you know like the C11 memory model, this is the same kind of thing, but just connected to sequential code, not even concurrent code. So I don't have time to get into a lot of details here, so I'm just going to give you a small flavor. What we'd really, really like to do is have a better story than C and C++ here. It is actually incredibly difficult to validate that a piece of C++ code follows the C++ memory model. There's so many little things you can get wrong that essentially mean the optimizer could do arbitrary things to your code, like all bets are off. And there's something very promising in Rust, which is we have a declared boundary between safe and unsafe code. And so there's this intuition, and this kind of comes back to this earlier question, that like the vast majority of code is written in safe Rust. We ought to be able to trust all of the types for that code and optimize very strongly there. And then we're just more careful in optimizations for the bits of unsafe code, right? And so this led to something called the tipsypop model, where unsafe code is kind of this gooey interior where like you're fudging the types a little bit to try to make this work, and we'll see an example of this in a second. And consequently, the compiler's not optimizing very aggressively. It's conservatively assuming that you might be lying to it. But then there's a hard exterior, which is when you actually reach some kind of abstraction boundary, and you've said, okay, now this is a safe interface around this code. Now all the types actually mean what you think they mean. So this is very appealing, at least to me, in abstract, but it has a lot of problems. Number one, it's not very clear where exactly the line between the GUI and the hard candy should be drawn. Should it be a module, a function, a whole library? There's also the sort of unfortunate fact that with this approach, dropping into unsafe Rust loses a whole bunch of optimizations, which is kind of counterintuitive because you're usually doing unsafe things for performance reasons, right? So we're still sort of figuring out if there's some way to use this kind of approach. And some of the ways we've been exploring are alternatively taking a very type-centric view of things, where whenever you cross a function boundary, basically the types tell the full story and you have to live up to what the type says. A more lax story where you can lie at the type level for at least some of your code, as long as you don't actually do bad things that the types might suggest. So let me just give you, going back to this split function, some concrete examples of what I'm talking about to drive this home a little bit. So the thing is, to do this split, we somehow have to magic up 2 mutable references where we only had 1, and we're not going to get help from the compiler. Some of this notation is a little crazy, don't worry about it too much. I'm going to show you 2 different ways we might do this and talk about how both of them could be wrong. So here, what we're going to do is we just start by making an outright copy of the mutable reference we were given by writing some unsafe code. And the unsafe code basically says, oh, forget the fact that this was a borrow, turn it into what we call a raw pointer, which is like sort of over an unsafe land, not getting any help from the Rust compiler, and then unsafely take that new pointer you just made and call it a mutable borrow again. So now we just magicked up another mutable borrow of the original data, and then we go and pull out the slices from these 2 different copies of the reference, and then we return them. So I don't know, like, opinions vary as to whether this code is reasonable. Certainly in terms of what it actively does, it never uses these aliases that are floating around in a bad way. It's not, in fact, mutating during this aliasing that's happening, and by the time it returns, it's got these 2 non-overlapping mutable references, everything checks out for the type system. But there was this uncomfortable moment, right, where we had 2 mutable references that were overlapping. And maybe the optimizer does something with that information, right? It says, oh, well, these 2 can't possibly be aliasing, so I'm going to just reorder something. Probably nothing bad would happen to this particular function, but if you did this kind of thing in a more complicated setting, you could imagine the optimizer getting into trouble. Right, and so this is kind of what I mean about this trade-off of, like, this seems reasonable-ish to write, but actually, for it to make sense from the compiler perspective, we need to turn off the type system, essentially, and say, compiler, you can't trust the types you're seeing here because this code is unsafe. So that kind of sort of makes sense? So here's a more, let's say that we were trying to avoid the shenanigans of the last example. So we're going to try to do it right this time. So we don't construct a copy of the original mutable borrow. Instead, we move everything into raw pointer land. So we take the original reference, turn it into a raw pointer, we compute an offset, whatever, it's all good. And then at the end, we take these now distinct raw pointers and turn them back into mutable references, but they'll be non-overlapping. And so you might think, hey, we've done it. Like, we've written this whole function without ever breaking the type system. But actually, we still broke the type system in the sense that we had this whole time the argument sitting around that was a mutable borrow, and it overlaps with both of the slices we're returning. Right? So this is an open question. I don't have any conclusion here, but I wanted to give you a sense of how subtle this kind of stuff can be. And I feel a great sense of urgency here in the C and C++ world. All of these issues around optimizers on the one side and programmers on the others have caused massive headaches. And the more Rust code out there in the wild that we're optimizing or not optimizing in a certain way, the more our hands are potentially tied as to how we settle these issues. So it feels pretty pressing to actually nail down a model here, but it's really, really hard. Okay, Yeah.
So other than optimization, I feel that wouldn't this kind of code lead to like double free problem because you can't trace back like where was the pointer originally increased reference, and then when you go back you might try to free twice.
Okay, yeah, so the question is, not even thinking about optimizations, this seems bad because the compiler has lost track of where these references are coming from. Might something get freed twice or something, right? Because after all, we took one mutable reference in and we got two mutable references out. That sounds like it could spell trouble. So that's a really good question. And a lot of things in Rust sort of come together to make this work. So first of all, the fact that these are mutable borrows and not actually owned values means that neither of them has anything to do with destroying the data. So that at least is not a problem. And in fact, if we had written this, taking a vector in and giving two vectors out, that would be wrong, okay? But moreover, if you go back to when I was talking about lifetimes, right, the way this is going to be interpreted is we had a borrow of a slice coming in, we return two borrows, they all have the same lifetime. And that is a key thing that says to the compiler, look, you don't know where these borrows came from exactly, but you know that they're tied to this region where the original borrow came from. And so as long as these new references we've returned are around, you won't be able to access the thing that was originally borrowed. So that's what it allows the compiler to kind of lose sight of exactly what's happening, but still have enough information about regions to prevent the kinds of problems you're worried about. It's pretty tricky stuff. Okay, so Zaina, or one of the admins, I noticed that it's 8:15. I have a lot of talk left. What would you like me to do? I continue. Okay. Very good. If anybody needs to leave, I won't be offended. All right. So that was all just the first half. I would say this one would be faster, but I'm probably lying. Okay. So I said at the beginning that Rust, basically has these two core concepts: ownership, which we've now seen at quite a level of depth, and the trait system, which is how we do abstraction in Rust. So I'm going to walk you through traits fairly quickly. Traits are way more straightforward than the ownership stuff we've been talking about. A trait is just an interface. So it's a description of some things that a type or set of types can do. If you know type classes in Haskell, then you basically already know most of this story. There are some differences, like we have notion of methods around traits. And I'll talk about some of these other aspects as we go. Okay, let's just dive directly into an example. So here's a trait from the standard library. So the first thing to notice is, we're defining this interface sort of completely independently from any type. And we'll see in a second that you then provide a separate implementation of this interface for whatever types you're interested in applying it to. It's not like a language like Java where all the interfaces a type ever supports have to be declared up front when you define the type, like in the library defining the type. Rust actually lets you define a trait downstream from a type, so you can use some library that's defining, say, network sockets, and then you can define some trait and implement it for that existing type. Okay, so we have a trait. We will subsequently implement it for different types. Within this trait, we have some other types flying around. So an iterator might apply to something like a vector, but then there's a distinct type of the items of the vector that you're actually iterating over. And then here we see our first method signature. So I alluded to this before, but there's this special notion of self. And by writing &mute self, we're saying to call the next method, you have to have mutable access, and a mutable borrow will be created automatically. And then you'll get back possibly an item or none if you've exhausted the iterator. So we can just briefly look at an implementation. Here's a range structure, so it's just an iterator going, from a from value to a to value inclusively. There's nothing particularly interesting about this, but like I said, it could be that range was defined in one library and the iterator trait and this implementation was defined in some other library. They don't all have to be done up front. Okay, questions so far? This should be pretty straightforward. So, so one interesting thing about traits won't be super relevant for the rest of the talk, but it's worth pointing out. We get a lot of mileage out of traits because we use them for both static and dynamic dispatch. So the way this looks is, if you have a function like this is static dispatch. This is saying, please statically give me a type T that implements the iterator trait, and then I'll use that type internally. And right, so this is generics or parametric polymorphism, take your pick. And the neat thing about this is Rust's compilation model means for each different choice of T that ever comes up in your program, you'll get a custom compilation of U's that's specialized to that type. And that enables all kinds of optimizations. So this kind of thing you also get with templates in C++, and in both languages, it's used very, very heavily to guarantee certain optimizations for libraries that you create. On the other hand, sometimes you want dynamic dispatch. So here you're basically saying, I don't know statically what actual type I'm getting. I just know that it implements the iterator trait. And I won't be specializing U's for each different type. Instead, it's just expecting to get a reference to whatever, some type that implements iterator at runtime. So dynamic dispatch always has to happen behind a pointer, and that's because you need a uniform representation. Like types themselves could have all kinds of different sizes and layouts. But here we're going to compile U's just once, and it needs to work for all types, and the only way to do that is through indirection, through having a pointer. Okay, I won't belabor this because yeah. So you for the first function, yeah, you could literally just write ampersand T. That would be a reference to T. So the difference is, using the angle brackets and generic syntax, we're saying pick a specific type T, and then you get the rest of the signature. Whereas with the second signature, we haven't named some abstract type. We're saying the type ampersand iterator. It's exactly. Okay, let's not spend too much time here because it's not super relevant to the other parts. So one of the neat things that the trait system gives you, and this is very familiar if you've done much Haskell, is the ability to automatically compose implementations. Right, so Rust has a clone trait, which is how we do deep copies of data. And we have sort of composable implementations, like if you have two types, each of which implements clone, then we can provide an implementation of clone for the pair of those types, right? And we just call recursively the clone implementation on each part, right? That's really straightforward. And we do this kind of thing for lots of data structures like vec and so on. Anything that could take a generic argument, we tend to have these kinds of implementations. And that leads to some pretty interesting results. So sort of summarizing a few implementations we have. So we have the one for pairs, for vectors. Then we have just leaf implementations for built-in types like U64 and string. And from this, we actually get an infinite collection of implementations, right? So we can deduce that U64 is clone and string is clone. But then using the composition, we know, oh, well, vec of U64 is clone, and pair of U64 string is clone, and so on and so forth, right? We can build up arbitrarily complicated types and deduce that they implement clone because of these composite implementations. And the reason I want to harp on this is, there's a well-known relationship between type classes and logic programming. And don't worry if you don't know what that means, I'm going to explain it. But basically, we can reframe what's going on here in a slightly different way by expressing it in logic and essentially saying those composite impls, what they're really saying is, for all types T and U, if T is cloned and U is cloned, then T and T comma U is cloned, right? So it's like a logical implication and a universal quantification and so on at the logic level, right? Hopefully this is fairly intuitive. If you don't know too much about logic, that's fine. But I want to sort of quickly, here I'm going to go much more quickly to the research side of things. So this connection, like I said, is sort of well-known folklore. But recently, we've started taking that view much more literally in Rust. So we've been working to rewrite the trait system in Rust to actually use a logic programming engine. So basically, the existing trait system was coded in a sort of direct way and had all kinds of limitations. It was really hard to extend in some of the ways that we wanted to. And so what we're doing is sort of decoupling things a bit. So we have this engine called Chalk that implements something like Prolog, but it's extended in various ways. And the core thing is that the stuff you're doing with traits in Rust sort of exists at one level, and that stuff gets compiled down to a logic program. And then we answer the questions we need to answer to do type checking and code generation and so on by asking this logic engine questions about this lowered version, this compiled down version of the code. And that might sound kind of complicated, but it's actually really, really nice in practice because it allows us to abstract away a ton of detail about Rust-specific stuff and view the core trait system just in terms of logic. And so as we've wanted to make various extensions to the trait system, we can go pull the handbook of logic programming off the shelf and find a chapter that talks about that kind of extension, implement it, and then use it in the trait system. So this is very much active work right now. And there are all kinds of questions floating around. So a very basic one is just, well, what logic do we actually need? That's much less clear than you might think because there are a lot of subtleties around Rust's traits and a lot of extensions we want to make. This is, just to be really crisp about this, sort of my perspective as an ex-academic and now working here, right? We don't have time to do a really thorough job of doing a literature search and figuring out, oh, it's exactly this logic and maybe we need a custom logic and we need to prove all these things about that and so on. We just can't afford to take that amount of time on solving these kinds of problems. But we know that these things exist out there, and we're kind of coming to folks like you, begging you to spend the years potentially that it might take to really bottom this out and very crisply formalize the logic that we need and the fact that it's sound and so on. So even the basic question about what logic, how does that logic work and so on, and then there are a host of other questions around extensions we want to make. So I'm going to just talk briefly about two particular questions in this area. Again, mostly just to give you a flavor, maybe spark some interest. So the first one is something called coherence. Right, so I was talking earlier about how you are allowed to define a trait and then implement that trait for types that already existed, right? So you can apply new interfaces to old types. But if you just let that sort of thing go crazy, you might imagine, oh, anybody could implement any trait for any type. Couldn't that result in multiple implementations of the same trait, the same interface for the same type? And then what would happen? And so this property of coherence is basically saying we need to prevent that from happening. We want it to be the case that if an implementation exists, there's always a unique one. And as part of that, you should be able to add new dependencies to your project, bring in new libraries without that ever breaking your code. And that might seem like kind of a non sequitur, but the point is, if any library could add any implementation, and we wanted to rule out these conflicts, then it could be that, well, just the act of bringing a library into your project could break your code, right? And we don't want that either. So that's what we're trying to achieve. The way that we do this is through a couple of rules. We say, so there's the no orphans rule that says, basically, if you're gonna provide an impl, you have to be the library that either defined the type or defined the trait, roughly speaking, one of the two. And if you think about it, offline, you can convince yourself that that's sort of enough to rule out a lot of these problems. And then within a given library, you're not allowed to overlap. So if you have generic implementations, they can't ever be instantiated to give you the same type for the same trait. Okay, so again, not important to get all of these details, but that's the kind of thing we want to model. Oh, yeah, question, sorry.
The no orphans rule still seems rather restricted to me. So if there is like a trait in the standard library, and I'm using another library where some types are defined that are not implementing clone,
yes.
I can't implement clone, that's right?
Yes, that's correct. And this is a headache in Haskell as well. And there are various workarounds to deal with this kind of thing, but basically, yes, that is the big pitfall. But it's still better than Java in the sense that,
Scala, where this thing is managed through imports?
I'm sorry? Oh, yes, so, right, so there are other approaches where you might take a less global view of which impls are available, but that's not the approach we've taken in Rust. Other questions about coherence? So there's some very interesting subtleties here. And this has to do actually with an area that comes up a lot in Rust, and I feel like I rarely heard talked about in academic circles, which is, when we think about programming and programming language design and so on, it's important to not just think about the first program that you write, or sort of the initial version, but also think about the ways that APIs evolve over time and whether the language provides you with tools to make that evolution work well. And so let me show you an example of what I mean. So here we have two different libraries. Libraries are called crates in Rust. So we have a foo crate, which just implements a type called foo and doesn't impl clone. Then we have another crate that depends on foo, and it creates a new trait bar, and it wants to provide these two implementations, right? One, an implementation of bar for everything that's clone, and then a direct implementation of bar for foo, which is not clone. Okay, so on the one hand, this follows the coherence rules. Like this doesn't lead to any problems in that sense. It's unambiguous which impl to actually use because foo is not clone. On the other hand, if you're writing a library, generally your expectation is, well, okay, once you've made a version of the library that exposes a given interface, you can't take that interface away, but you should be able to add new interfaces, right? That's a basic expectation that libraries can grow over time. So it would be very reasonable for the foo crate to add a clone impl for foo later. But if it did that, the bar crate would break in that new version, right? Because now all of a sudden the overlap rules would come into play. And we'd have a conflict between these two impls. So this is a very interesting phenomenon, and this kind of thing comes up over and over in Rust and all languages, and I think it's really important to think about it. So the way that we think about it, this particular case in Rust is we're doing this kind of negative reasoning in bar, where we're saying, oh, well, foo does not implement clone, therefore something. And negative reasoning like that is always dangerous when you're reasoning about a different library that you don't control, because things could change later, right? Implementations could be added later. So we actually don't allow you to write the bar impulse here, basically because we say that foo does not implement clone today, but it could tomorrow. And I'm not going to take the time to explain modal logic, but if those of you who know about modalities, to connect this back to the logic programming thing, I think there's a really interesting way we could approach it, which is to think about working in a modal setting. So I said I wasn't going to explain it, but I mean, basically, like in a modal setting, facts are not true or false everywhere. They're true or false relative to sort of a possible world you're existing in. And so we think about this possible world as the set of implementation that exists at a given point. And if you're in one world, you could move to a new world where more implementations are added by the crates you depend on. And so with that view of things, right, in modal logics, there's generally a way of saying, I want to prove this thing not for just my current world, but for all possible worlds I could reach from it. And that's exactly what we're trying to say with this coherence to sort of make sure that adding an implementation can't ever break downstream code. So again, we don't have time to actually work this out in any formal detail. I think it makes sense. I think it's kind of neat, but it would be really cool to actually sit down and build out a logic and prove that any of these properties hold. Okay, last thing. So I mentioned this no overlap rule, but we would like to relax that rule. So here's code we would like to allow, where you have some trait and you have a kind of general implementation for any clone type, but then you would like to provide a more specialized implementation for string in particular, even though string is clone, right? So both of these implementations would apply to string, but the idea is that the one that's specific to string is more specialized and the compiler should prefer it. And so we can come up with a scheme for always having an unambiguous choice of which impl is the most specialized that applies, and then we still get our coherence property. So the exact way that specialization might work is not super important for the research problem I want to bring up. But so we talked earlier about lifetimes and the fact that lifetimes are part of these reference types that you often don't write, but they are there. And those lifetimes are really important. A type ampersand tick A vec event and ampersand tick B vec event, those aren't compatible things. And if you get them confused, you will get memory safety violations, right? We have to keep careful track. But at the same time, we don't want those lifetimes to influence the runtime behavior of the code at all. So I mentioned before about monomorphization, how, or static dispatch, the way that we specialize code for different types. That's true, except when it comes to lifetimes. So if you pass in ampersand tick A vec or ampersand tick B vec to a generic function, that's going to generate just one copy of that code that works for any reference to a vector, because the runtime behavior and the runtime layout and all of that can't possibly depend on the lifetimes. Right, so we say lifetimes are erased during compilation. And that's all very good. There are lots of important reasons we want to do that, but it's also a big headache for specialization. Because you might write something like this, where you're saying, I have an impl that works for literally any type, and then one that is specialized for types that are tick static, meaning that they don't have any non-static lifetimes appearing, no borrows inside these types. We can't allow this, because the type checker will sort of have lifetime information and reason about things in that way, but then when we go to generate code, we will have lost all that information and we won't know which of these impls we should be using. And so we'll sort of go off the rails. Type checking and code generation won't match. And this turns out to be just incredibly subtle, right? I mean, this first example is like, pretty obvious. You might say, oh, well, you just shouldn't be allowed to write like tick static or something. But it turns out you can create situations that look much more innocent, where you have one crate that's doing some specialization, right? Where it has, so the bar crate has a general impl of bar, and then one that's specialized for types that implement foo. No lifetimes in sight here. You're not talking about lifetimes at all. Then you have this other specialization at all, but it is making an implementation that requires tick static. And if you put these together, you get the same problem. And it gets worse. Even just repeating a type multiple times is enough to create these kinds of problems. Because again, if we end up passing a reference type into this, we can't tell if we actually have the same lifetime on both sides once it comes to generate code. So this is actually a piece I've spent a lot of time working on, and we have an implementation of specialization, but we haven't actually shipped it because we know it's not sound because of these reasons. And we think we see a path to soundness, but we're not sure. Help? Okay. All right, so that sort of sums up the technical pieces. So let me wrap up real quickly just by taking a higher level view of all this. So there's a ton of research going on around Rust, some in academic spheres, some in spheres we wish were academic, but we don't have the time to do it. One of the most important is the Rust Belt project by Derek Dreyer's group. That project has shown soundness of the Rust language, or at least a core version of it, but it also gives it a model for showing that unsafe abstractions are safe, like the kinds of stuff we were showing before with split, where you are using unsafe internally but claiming to provide a safe interface. There's actually a logic you can use to do that kind of verification. With a big caveat, it doesn't reason about any of these optimizations, right? So all these questions we were talking about raw pointers versus multiple ampersand mutes floating around, it's not covered by Rust Belt at all. It would happily accept any of those implementations. So it's a good step, but it's not enough, right? And so the next phase in that project is what we've been calling the unsafe code guidelines, and that's basically that first big research problem I talked about of how do we balance between optimizations and the ability to reason about code and actually set out a model that people can use. And Ralph is a student of Derek Dreyer, so it's all sort of coming from the same group. There's the Chalk project I just talked about extensively. I think Diane, did you talk about the verification stuff earlier? Tomorrow. Okay, so Diane will be talking about that stuff. That's incredibly exciting. There are a bunch of groups doing verification projects around Rust. I'll let Diane cover that. And then it just goes on and on and on. There are other areas of the compiler where we're doing things like Chalk, where we're trying to decouple and rewrite the borrow checker to actually use a sort of data log engine internally. You can read this list, and I'll send the slides to Zaina. She can distribute afterwards. And a lot of these things have very extensive blog post write-ups. So like if you wanted to jump into stuff related to Chalk or the unsafe code guidelines or whatever, there's actually blog post series that show all the steps we've taken so far and also ask for help. So to sort of conclude, as I said at the beginning, Rust is really exciting for a lot of reasons. One of them is that it really does manage to blend academic and engineering points of view. And so we care about soundness. We would like to formally model all of these things. We can't do it all on our own, though. We have to partner with academic groups, but there's a huge opportunity there. And Rust is becoming a pretty major language. So it's broken into the top 15 languages used on GitHub, which puts it ahead of Haskell and Scala and close to overtaking Swift. So in terms of making an impact on the world, this is a serious project, right? This work here academically actually can have an impact on the programming world that's pretty substantial. And finally, it's worth saying we care a lot about the community aspects of Rust and having a friendly, inclusive community. So, it's a great place to come in and get started, whether you're doing research or not. So come say hi. Thanks, everybody. I'm happy to take, yeah.
I will also say we're going to be doing kind of a relaunch of the unsafe code guidelines in the near future, sometime between now and RustFest, which is in August in Portland.
RustConf, yes, mid-August. Yep. Too many conferences.
Yeah, so basically what we're doing is we're trying to gather these questions and identify the pitfalls and ways that you can do it.
Yep.
In a less terrible way, because there are some really terrible things people do.
Yeah, so in other words, this is a great time to get involved if you're interested in any of this stuff. Other general questions or comments? Yeah.
So you kept reiterating that you guys can't solve all of these questions, and is that, my question is why? Is that like an issue of the team being too small, or the funding not being enough, or?
Great question. Yeah. So to repeat for video, the question is basically why is it that we can't afford to actually prove soundness of all these things? So I think, I mean, a lot of the reasons you suggested are true. It's sort of a combination of all of them. I think bottom line is the Rust team is driven first and foremost by making Rust successful at what it's trying to do. And while the safety guarantees are a huge part of that, we can't prioritize them above everything else. In other words, if it comes to being absolutely 100% sure versus being able to ship this year versus 5 years from now, that's just a clear choice for us, that it's more important to start getting adoption and growth. But we have a strong understanding in the Rust community that if soundness holes are discovered, we will address them and fix the language, and that has happened in the past. So that's part of it, is just trade-offs. No matter how big our team was, we would always have to be making those calls. I think there's also just aspects of some of this research that are interesting from a research perspective and maybe aren't so critical for doing what we need in Rust, but still are worth pursuing just for the sake of the knowledge. You know what I mean? Like an example of that would be, if you look at Chalk and the logic programming we're doing, like relating that to the existing literature on logic programming and figuring out, okay, exactly which logic are we doing and so on. That feels like a valuable thing to do that the academic world should do, but it's not critical for the soundness or shipping or something like that in Rust. So that, I mean, we definitely have people who would be capable of doing this kind of work, but it's just the trade generally doesn't allow us to. Anything else? Yeah.
With the browser engine you're making in Rust, is there a particular example where you've rewritten a feature and then you look at the Rust code and you look at the C code and you're like, yeah, this is hands down was worth it. This is amazing.
Yes. The CSS styling system was wholesale replaced with Rust rewrite called Stylo, and there's a blog post on the Rust blog that's like fearless concurrency in Firefox Quantum or something like that. And just two things to say about that. Number one, it's about half the size of the C++ code it replaced. Number two, it is a parallel styling engine, which was something that was attempted multiple times over the years on the C++ code bases and always failed, because concurrency in C++ is really hard, and it was essentially a breeze in Rust. So it's hard, I don't know that anybody knows both code bases enough to do and we're talking about 75,000 lines of Rust, right? But certainly in terms of the bottom line, we were able to wholesale replace this. It works great, the performance is amazing, and it let us do this parallelism that we wanted to do for a long time, I think a lot of that is clearly attributable to Rust. And I mean, this fearless phrasing, like that's a big part of how we frame Rust, that because of the safety guarantees, it allows you to be much more ambitious in what you are doing in your programming than you typically would be for systems programming. So you don't have to be afraid of concurrency in Rust because you know the compiler. And I think that's really important. Yeah, Diane.
The answer to that is also on the safety side, yes. There is going to be a forthcoming paper basically analyzing security-related bugs in the styling system and looking at whether or not Rust would have prevented them if we could take a time machine and go back and start in Rust. And the answer is 73% of the security bugs should have been prevented.
That's a better answer.
Well, that's because I just read the paper.
Yeah. Cool. Yeah.
How much of the ownership overhead is erased by the compiler during code generation versus carried forward into the runtime?
Sorry, say that.
It seems like there's a lot of metadata ownership properties would need to be carried forward as code being compiled. How much crosses that barrier into the runtime?
Yeah, it does. So yeah, so for the video, the question is basically, what is the runtime overhead of all this ownership tracking we're talking about? So for all the stuff I showed you today, the answer is no overhead. So all of, it's essentially just type and borrow checking. And after those phases of the compiler are complete, all of the ownership information is thrown away. There are, going back to one of the really early questions around what if ownership patterns are dynamic instead of static. So there are library types you can use that do move it to runtime, but that's always an opt-in, and those are relatively low cost. For which bounds checking? Array bounds. Yes, there is. Sorry. So the question was, do we do runtime bounds checking of arrays? Yes, we do. And there's a longer answer about how most of the time that ends up not actually hitting the compiled code because you're using iterators or other things. But yeah, there is definitely some runtime overhead for safety, in general in Rust. It's not completely free.
Any chance it will change in the future?
So the question is, could we get rid of even that overhead? Yes, potentially. It's a little hard to predict. There's work right now in what we call constant generics. So basically letting you use runtime values in the type system. So you could talk about the length of an array statically. That leads to a very, very large area of work with dependent types and so on. And it's hard to say how far Rust, the language, is going to go down that track versus external tools or whatnot. But it could be that something like that helps you remove the overhead. In practice, I'm not aware of the baseline overhead for safety being a problem for anyone. If it's ever in a hot loop, then you can use an unsafe escape hatch and just convince yourself yeah, this array bounds is okay. Okay, Zaina's telling me we should end. Thank you, everybody.